Okay, I want to revisit the last problem that I did. I want to do this one in general instead of with particular numbers. So I have a car of mass m traveling with speed v in a circular track of radius r. The difference between this and the last problem is that in this case, the track itself is not horizontal, but is banked. And it's banked to some angle. Oh. Theta. Okay? So, choose a body. I choose the car. What are all the forces on the body? There's its own weight, mg. There is a normal force now which points in this direction. Okay. And I'm going to say that this is an icy track. Okay? And so the center of the track is over here, but the track is icy. In other words, the friction is 0. So mu equals 0 in this case. Okay, now we want to choose a coordinate system. Now, this sort of looks like an inclined plane, doesn't it? We're all used to doing the inclined plane problem and choosing a coordinate system where, let me just mess with this for a minute, where one axis is like this and one axis is like this. And what we want to say is, well, is that the way we want to do things now? And so let's think about it a minute. Why did we do this before? The reason we did this before is because the acceleration was along the track, okay? And the object was in equilibrium in this direction, okay? But that's not the case here. Now the acceleration points in this direction, okay? And so the object is in equilibrium along the vertical direction, but it's not in equilibrium along the horizontal position. Okay, so let me clean this stuff up a little bit here and go back here, get this squared away. Let me just neaten this all up here. Just sort of start over again drawing things. Okay, so we've got mg like this, and we've got n like this. And those are all the forces that we have now. And so now we're going to choose a coordinate system which has its x-axis like this and its y-axis like this. And recall that this is theta here. Okay, so we're ready to go. We've chosen a coordinate system. We better be careful here. Let's see, make sure that we find out that theta is here. And so the two components of n are like this. So here's n sub x, and here's n sub y. So the sum of the forces in the y direction is equal to 0. It's in equilibrium in the y direction, because all the acceleration is the centripetal acceleration. Okay, the acceleration is here, v squared over r in this direction. Okay, so the sum of the forces in the y direction is equal to n cosine theta minus mg, which tells us that the normal force has got to be equal to mg divided by cosine of theta. Sum of the forces in the x direction is not equal to 0. It's equal to m times the acceleration, which is v squared over r, and that's equal to n sine theta but we know what n is. Okay, n is mg over cosine theta, and sine theta over cosine theta is the tangent of theta. So we finally have that v is equal to, okay, the velocity that you can go through this if there's no friction, the velocity you can go around this particular track, even with zero friction, is equal to, let's see if I can do my, first of all, it doesn't make any difference what m is. You notice that m cancels out up here. Okay, that's kind of interesting. This thing will work just as well for a motorcycle as it will for a Mack truck. So v is equal to the square root of rg tangent theta. And that's the kind of thing would be handy if you are a civil engineer and you wanted to make a highway and you wanted to figure out a sensible angle at which to bank it. Okay.